Today's lesson comes from Systems of Equations, Graphing Systems, 3 Types of Solutions. Our essential question today is, what does it mean for a coordinate to be a solution, and how do we identify each of the 3 types? Please take a moment, pausing the video if you need to copy the topic and essential question into your header, along with today's date, set up your question column and your note column, and resume the video when you're ready to begin. So as we are just beginning our work with systems of equations, I want to take a moment, have you copy down some vocabulary that we will be using as we discuss the types of solutions when graphing systems. So the first is, what do we mean by systems of equations? Well, that's when we're analyzing how 2 or more, that's why there's a plus sign here, 2 or more equations relate to one another and or compare. So this could be in real life situations, comparing 2 companies and the cost of doing business with them, or we could just be looking at 2 linear equations out of context and trying to identify what they have in common and what they don't. We will talk a lot about solutions to these systems, and so it's important to understand, first of all, what a solution is to any linear relationship or equation, and then secondly, how it applies to systems when we're looking at 2 or more equations. So let's just think about what we mean to a solution to any equation. When we're talking about a solution, we're talking about an ordered pair, values for x and y, that make an equation true. So that when we substitute, so we're talking about equations that have the variable x and y in them, and that when we find a number for x and a number for y that we can substitute in or look at on the graph and it makes the equation true, that would be a solution to that one equation. So what do you think that means when we're talking about a system of equations? Well, if you were talking about a solution or an ordered pair to a system that makes both equations true, then I would agree. So it's a point that is true for both equations. So today we're going to focus on understanding systems and solutions to them to see the 3 types that we're going to run across in our work in this unit. Let's go ahead and get started. The first type of solution we'll see is one solution. So let's take a look at a graph. You'll want to set yours up, but let's go ahead and enlarge that so you can get a better detailed graph going. Okay, so here's an enlarged graph. You'll want it to go from at least -1 to 4 on the y-axis, and from -5 to 5 on the y-axis. So go ahead and get your graph set up. And then we're going to graph the equation y equals 1/2 x plus 3. So once you get your graph set up, go ahead and graph this equation. Okay, it should look like this. Our b value is 3 and it goes up 1 over 2. So here's the graph of our equation. So what does it mean to be a solution? Well, that would be any point on the line that, if we're looking at it in graph form. And so, for example, we might use the point -2, 2. Go ahead and find that point. Yeah, there it is. So it is a point that is on the line, so we'd say it's a solution, and we can verify that algebraically. If we took this x variable, -2, and we put it into our equation and did our calculations, half of -2 is -1. And then if we add 3 to that, y would equal 2, right? Our y value is 2. So this -2, 2 is a solution to this equation because on a graph we see it falls on the line, and when we plug those values into the equation, it makes a true statement. So what does it mean to have one solution to a system? Let's add another line to this graph. So I've gone ahead and added the green line here, y equals -x. So it has a -1 slope, and it has no b value, so it starts at 0, it goes down 1 over 1, And so here's the graph of that line. And if you notice, this green line, y equals negative x, also goes through the point negative 2, 2. So because we are now looking at two equations on the same graph, right? We have the blue line and this green line. That's a system. And this is an example of one solution to that system because negative 2, 2 is the intersection point where these two lines meet. And they only meet one time. So this system has one solution. So to recap on one solution, if we're looking at just one line, it is a coordinate point that falls on the line and makes that equation true. As we looked at with the point negative 2, 2 in the equation y equals 1/2 x plus 3. If we're talking about what it looks like for it to have one solution in a system, it is the intersection point. So if the two lines have a point where they cross, and they cross at exactly one point, as is with these two lines, crossing at negative 2, 2, then this system has exactly one solution. One point that will make both equations true. Let's go ahead and take a look at our next example, no solution. So this is the graph we're going to use to look at no solution. So I'm going to go ahead and zoom in so you can get a good look at how to set up your graph, and we can start to examine what a no solution would look like. Okay, so this is the graph we're going to use for our example for no solution. So go ahead and get your graph set up with the x and y scale, and the first equation that we're going to graph is going to be y equals negative 3x plus 4. So again, set your graph up, go ahead and graph this line. Okay, your line should look like this. It should start at 4 with our b value of 4 and go down 3 over 1, down 3 over 1. So lost where I was there. Alright, and we want to kind of look at this point. So let's talk about, again, what a no solution means. So if we look at the point 1, 3, find the point 1, 3. Is that a solution? Okay, well, if you said no, you plotted that point 1, 3 here. Again, this is no solution because it is not on the line. So when graphing, that's the biggest indicator. And if we plug 1 in for x, we would get negative 3 times 1 is negative 3. And negative 3 plus 4 is 1. That doesn't equal 3. So again, easiest way to see it on a graph is that that point is not on the line, so it's not a solution. But what about a no solution to a system where we have a set of lines graphed and we would classify them as no solution? What do you think we're going to see? So to make this a system, I have added another line here. We have the line y equals negative 3x minus 2. Looks like this. Starts at negative 2, and if we find 2 points, it drops 3, runs 1. Same as this one. Drops 3, runs 1. So these two lines, remember in our last example we said a solution to a system or two equations on a graph is where they intersect. Will these two lines ever intersect? No. If we notice, they actually have the same m value. So the m value here is negative 3, and the m value on our second line that we added was also negative 3. And so they have the same slope, so they're always going to travel at the same rate of change, but they have different b values. So they start at different places, which means they will never touch. So parallel lines will always give us a no solution when we're talking about systems. There's no point that falls on both of these lines at any given time. So to recap, if we're talking about no solution, for looking at just one equation, we mean that the coordinate point is not on the line, like as in the case with 1, 3 here, was not on this blue line. The equation y equals negative 3x plus 4 did not make that equation true. And then when we look at it as a system, we're talking about no solution because these two lines don't have any coordinate point where they will intersect. There's no point that will make both of these true at the same time. And so when you have a pair of parallel lines, you're going to get a no solution for that system. Let's go ahead and take a look at our third and final example, infinite solutions. Alright, so again, we're going to look at our final example, and here's the graph we're going to use. Let's zoom in to get a better look. Okay. Here is the graph we're going to use. Get your scale set up, and the first equation that we're going to look at is y equals negative 2.5x plus 4.5. So getting your graph set up, go ahead and graph that line. Your graph of your line should look like this. It is starting at 4.5, somewhere here in the middle between 4 and 5, and it is dropping this half and 2, so 2.5, and going over 1, dropping 2.5 and going over 1. So we get this line here. And so we're just going to go ahead and add another line. Let me give that to you here. It's going to be y equals negative 1/2 times the quantity 5x minus 9. What do you think that might be? Well, first of all, we really haven't dealt with any equations here that have parentheses, so I'm going to go ahead and unveil it and just show you what the graph of this line is, see if you are correct in any of your guesses, and then talk about what that might be and why. Okay, so I've used the black dots to show the graph of the line y equals negative 1/2 times the quantity 5x minus 9, and if you notice, it's right over top. It's the same points that make the line y equals negative 2.5x plus 4.5. So why do you think that might be? Well, if you said that you noticed we could use our new skill of that we've been reviewing of using the distributive property here, and you multiply negative 1/2 by each term in this parentheses, we're going to end up with y equals negative 2.5x, because negative 1/2 times 5x is negative 2.5x, and a positive 4.5 starting value, because negative 1/2 times negative 9 is a positive 4.5. So they disguised it, but what it is it's actually the same equation, just written in a different form. So in this system, we're graphed the same line. So when you graph the same line, you end up with two lines that overlap each other, and therefore they share every single point. These black points are just some of the points on the line. There's an infinite number all connected together to make that straight line. So a solution to a system that has infinite solutions, whether they're written exactly the same or disguised, is when you have graphed two of the same equations. So to recap, infinite solutions refers to overlapping lines, meaning you graphed two or more of the same equations, and therefore they always share every point on the line, an infinite number of solutions, as we saw with these two equations. So there you have it. There are the three types of solutions. Please make sure that your notes are complete with accurate graphs that include the x and y axis scale and a summary that answers the essential question in your own words.